Yes, the light.
Hi, good evening, everyone. Happy New Year to you. Glad everybody's here. I got sick for 2 weeks. Anybody else? I was one of those. Yeah, I even had a shot. But well, glad you're here. Brave the cold. The rain's gone, which is nice. It's relatively cold. Yeah, okay. So welcome to Lunar and Planetary Institute. My name is Andy Shaner. This is this is our third presentation in our series on ocean worlds in our solar system. Tonight is Enceladus. Our next topic in February is Titan, and then still nailing down a date, but April or May, we'll have a speaker from JSC talking about the TRAPPIST-1 system, the exoplanets, and talking about the idea of ocean worlds outside of our own solar system. How do we know that? What do we look for? What does it mean? So that should be a really fun one. Speaking of Happy New Year, it's 2018, and this year is the 50th anniversary of the Lunar and Planetary Institute. I've only been here for 8, but I was instrumental in all 50, I'm sure, to some degree. It's been here in Houston the whole time, which is good. So hopefully we can continue that even well beyond 50. If you are a teacher here with us tonight, welcome. We have professional development certificates for you at the front desk, so grab one of those before you leave. It's only an hour, but hey, it's an hour. If this is your first time here, and even if it's not, and you don't get our emails, we have a sign-up sheet by the front door. Just add your email to that list, and we'll make sure we get you on our listserv so you're aware of our upcoming presentations. So now we'll bring up our director, Dr. Louise Proctor, to tell you about tonight's speaker.
Thank you. So very excited to welcome our speaker, who's kind of lurking back there.
I'm lurking, yeah, that's right.
Jonathan Lunine is a professor at Cornell University, where he is the David C. Duncan Professor in the Physical Sciences, and he's also the director of the Cornell Center for Astrophysics and Planetary Science. Jonathan is interested in how planets form and evolve, what processes maintain and establish habitability, as in whether they are a habitable world, and whether life might be present beyond Earth. He's been involved in several missions. He was a scientist on Cassini, which of course sadly ended in September. He's currently on the Juno mission, now in orbit at Jupiter, and he's on the MISE instrument. This is an infrared spectrometer on the Europa Clipper mission, which I'm also on, and one of our other visitors tonight, Hunter Waite, is also on that mission. And those of you who were at Bob Papalardo's talk a couple of months ago, he spoke about the Europa mission, so that's the one we're talking about here. Jonathan is also an interdisciplinary scientist on the James Webb Space Telescope. He's focusing on characterization of extrasolar planets and Kuiper Belt objects. So he's all over the solar system in a very exciting way. But we're also very happy to have him here because he was a summer intern here in 1979 and in 1980, right at the very beginning of his career. And he has obviously gone on to do fantastic things. So we're very excited to welcome him back.
All right,
Thank you very much, Jonathan.
Thank you. Louise and Andy, thank you very, very much. And it really is a pleasure to be back here. When I was a summer intern in 1979 and 80, LPI was in the old Jim West mansion. But still, when I come back to this building, I feel that spirit of that program, which really launched my own scientific career. I can't really overstate how important it was to me, and so I have very fond memories of it. Tonight, I want to try to convince you that thanks to the results of Voyager and Cassini, we know of one place elsewhere in the solar system today, without any additional information, where we can say there is an environment that can sustain life, and where we know how to go and actually look for life that's present in that environment. We can do it today. And that place is Saturn's moon, Enceladus. It's one of several ocean worlds that you've been hearing about in this series. And it is the one which I think many of us in the scientific community agree we know the most about in terms of the nature of the ocean and whether it can sustain life. Now, it's a very small moon. When you look at a size comparison, as in the upper left, which shows the Earth, our own moon, and then Enceladus below it. Enceladus doesn't look all that promising. It's about 500 times smaller in volume than the Earth's moon. And indeed, the smaller an object is, planet or moon, the more easily it loses heat. So the smaller moons we expect to be colder, less active, and therefore less likely to have liquid water, which is one of the essentials, perhaps the central essential for life as we know it. But as I'll talk about, Enceladus is subject to an additional source of heating called tidal heating, which is thanks to the fact that it orbits very, very close to a very large planet, and that planet, of course, is Saturn. And so let me point out for you where Enceladus is in this right-hand figure. Here's Saturn. Here's the classical ring system. All of this is shown to scale. Here's Enceladus's orbit right here. And Titan, which you'll hear about in the talk after this one, would basically be over on the edge of the room or just beyond the wall. So Enceladus orbits very close to Saturn indeed. Now, it was discovered by William Herschel in 1789, and perhaps Enceladus's biggest handicap is its name. When I try to talk to people on an airplane or elsewhere at a party, and I'm invited to many very impressive parties, of course, as soon as I say that I work on Enceladus, I get a lot of frowns. It just doesn't have the cachet of Europa or Titan. You know, what is Enceladus? And a lot of people want to pronounce it Enceladus, really pronounced Enceladus. I'll get to the mythological name in a moment. It has a diameter of about 500 kilometers or 300 miles. It is indeed small. It has a density which is measured most precisely by flying spacecraft past it and measuring how much the mass of this moon changes the velocity of the spacecraft. And then, of course, we know the size of it, so the mass divided by the volume. That density turns out to be about 1.6 times that of water, which says that Enceladus actually has a lot of rock in it. In fact, it is mostly rock, the rest of it being largely water ice. And we know that that surface is water ice by looking at spectra of the surface. But there are other things present as well, which are very significant and which I will talk about. It has, because it's so small, a gravity about 90 times less than that on the Earth. That turns out to be key to having material actually pouring out of the inside of Enceladus into space, into orbit around Saturn, which can be sampled and was sampled by instruments on Cassini. It has a very short orbital period because it is so close to Saturn and because Saturn is so massive. It takes about 1.5 Earth days to make a complete circuit around Saturn. And that also is its day. Its spin and its spin period and its orbit period are the same. So on average, but not precisely, Enceladus keeps the same face towards Saturn. And the orbit is not a complete circle. We measure the degree of circularity of an orbit with a quantity called eccentricity. The eccentricity is 0 for a perfect circle. It's 1 for a parabola. This eccentricity of 0.005 would seem to be small, but it's enough to create effects that allow for heating of Enceladus and stable liquid water. Now, as far as the mythology goes, Enceladus, ironically, was one of the giants that decided to do battle with the Olympian gods, and in particular, Enceladus did battle with Athena, which was a really big mistake. And you see here in this depiction that Athena has pretty much done Enceladus in, and the legend also goes on to say that Enceladus is buried deep under Mount Etna, but we know that's not true. It's in orbit around Saturn. So the first hint that there was something unusual about Enceladus actually came from the discovery of a tenuous outer ring of Saturn in 1966 from a small observatory in Pennsylvania, Allegheny Observatory. Now, this is not a picture from that observatory. This is actually a Cassini image. And I'm showing this because the images really from the Allegheny Observatory are not interpretable. They're scientific data. They're not pretty. But this image of Saturn and the rings backlit shows very clearly Enceladus itself, somewhere down in here, and then this ring, this diffuse ring of material, which was named the E-ring of Saturn. And because Enceladus orbits within the E-ring, there was always the speculation that somehow Enceladus had something to do with the production of this ring. Now, not much else happened with respect to Enceladus until the Voyager flybys of the Saturn system in 1980 and 1981. And Voyager 2 in particular in 1981 made a relatively close flyby of Enceladus and made images that were quite spectacular. They showed that Enceladus is not heavily cratered the way you would expect a small solid body in the outer solar system to be. Once the planets formed, there was a large amount of debris left over that the planets then continued to sweep up for many hundreds of millions of years. Of course, we look at the moon, and particularly the far side of the moon is so saturated with craters that they literally overlap with each other. And that's true for some of the small moons and intermediate-sized moons of the Saturn system, but not for Enceladus. There's a part of Enceladus that does have a lot of craters on it, and there's another part that's very smooth, has no craters, and seems to be somewhat fractured. The Voyager cameras were 1970s vintage, so the resolution and the dynamic range, the ability to see light and dark, were far, far inferior to what's on your cell phone that you're using to take pictures of me now. And so once these smooth areas were seen, it became obvious, if you put that together with the fact that there's this diffuse ring of material, people thought maybe there is stuff coming out of Enceladus producing the E-ring, which then, as Enceladus plows through the ring in its orbit, recoats the surface and makes it quite bright. Enceladus is an extremely bright object. And a number of scientists tried to stretch these Voyager images to find evidence of a plume, and they could not. Now, about a year ago at the Lunar and Planetary Science Conference, which is held here in Houston and organized by LPI, there was a paper presented in which an image from the Voyager archives was found that seems to show a plume. There's some controversy about it. If in fact it really is the plume, then in fact Voyager discovered it. But for now, I'm just going to say that at the time that the Voyager missions were completed, there was no actual evidence for material coming out of Enceladus. And so that brings us to the Cassini mission, which was conceived after the Voyager flybys because the Saturn system was so interesting. The rings, the phenomena there, the atmosphere, Saturn's large moon Titan with its atmosphere, and the retinue of other moons, that it was felt that a natural follow-on to the Voyager flybys and a successor to the Galileo orbiter around Jupiter should be a Saturn orbiter, which came to be known as Cassini, was an international mission involving NASA, the European Space Agency, the Italian Space Agency, and a whole suite of other countries' space agencies providing instruments. There was a probe that was built by the European Space Agency that landed successfully on Titan. That's something that I was quite heavily involved in, but I won't be talking about tonight. You'll hear about that next time. And Cassini had on the main spacecraft, the Saturn orbiter, which was built by the NASA Jet Propulsion Laboratory, over a dozen instruments, which had a wide range of different capabilities. And it was that extensive suite of instruments that made it possible for Cassini not only to make spectacular discoveries, but to actually follow up on his own discoveries and make new ones. That's the remarkable thing about this mission. What we're usually used to in planetary science is that a spacecraft will make a very interesting and even profound discovery, and then we have to go back and figure out how we can get NASA to launch a mission to follow up on that. In a number of different cases, Cassini actually followed up on its own discoveries, which was really quite remarkable. It was a 20-year odyssey in space. 13 of those years were spent in Saturn orbit. Up on the top, you see the 13 years of the tour. The original design was for a 4-year prime mission from 2004 to 2008. These show the number of flybys of different moons in each year. Titan dominates because being the largest object in the Saturn system, the second largest moon in the solar system, with 1,000 times the volume of Enceladus, it was the gravitational slingshot for Cassini to allow Cassini to change its orbit to visit various different places in the Saturn system. And so to make that happen, the spacecraft had to fly by Titan essentially on every orbit. Now, the original 4-year mission was quickly extended principally because the spacecraft was working well and making discoveries, but also because Saturn itself experiences seasons as the Earth does. In fact, its tilt is about 26 degrees. The tilt of our own planet is 23 degrees. Well, my planet and your planet. We're all on the same planet. Most of us are on the same planet. And so what you see down here is the appearance of Saturn and its rings as seen from the Earth as it went through the seasons. Cassini arrived in the southern summer. The mission ended at the beginning of the northern summer. Saturn has a 30-year orbit around the sun, so the seasons are 7 years long. The satellites are essentially all coplanar with the equator of Saturn, so they experience the same season that Saturn does. And so there was a great desire to understand how Saturn, how Titan, and also Enceladus would vary with these seasons. So the project and the Project Science Group was able to convince NASA to extend the mission. Equinox refers to the fact that this was when the rings and the equator were aligned with the orbit plane to the sun. So that's the equivalent of fall and spring. And then several other extensions that took us all the way to summer in the north, by which point Cassini was out of fuel and the mission had to come to an end. It was early in the mission in 2004 and 2005 that the plume of Enceladus was discovered, and it was then there was then a gap because there was a strong desire, as I'll explain, to actually penetrate this plume and fly Cassini through it. But a lot of study had to be made first to make sure it was safe. And then of these other flybys of Enceladus, 7 of them involved actual flying through the plume itself. Now, the discovery of this plume is a little controversial. There were 2 teams that actually made observations simultaneously. They're very different observations. I'm not going to render my opinion as to who discovered the plume. It was discovered by Cassini. The first of these that I'm going to show you is a diagram illustrating what the Cassini magnetometer found. The magnetometer is on a long boom. It measures the magnetic field of Saturn. It measures the intensity and the geometry of that field. And Saturn's magnetic field very much is shaped like that of a bar magnet. I'm not sure how well you can actually see that on the slide. Fairly well. You can see how this is now a bar magnet underneath a piece of glass on which we've sprinkled iron filings. This was for a physics demonstration when I taught at the University of Arizona. And you can see the field lines coming out. And these are the field lines drawn for Saturn, very, very similar. But in the vicinity of Enceladus, that field was distorted. And the magnetometry team interpreted that as coming from a cloud of material that surrounded Enceladus that was being partly charged up by being bombarded by other particles, and being charged up could then deflect the magnetic field. And so that suggested that Enceladus was surrounded by either a symmetric cloud or, more likely from the data, a concentration of material in the south polar region. Around the same time, the imaging system on Cassini, which was much more sensitive than the Voyager cameras, began to take images of Enceladus lit by the sun behind it. So this is the sun essentially would be off to the side and behind the room, if you will. That allowed any dust that would be scattering light to scatter it forward toward the camera. And indeed, here in this image of the crescent Enceladus, you see material coming out. This is quite an impressive signature. And of course, if you then enhance the image, you see that it's actually an enormous plume of material coming principally from the south polar region. So here is Enceladus now not being backlit, but with the sun over here reflecting sunlight and so being mostly fully illuminated by the sun. You see in the south polar region these linear fractures that have the unfortunate Latin name of sulcus, or plural is sulci. The International Astronomical Union names all these things. They're the people who demoted Pluto. I've had no desire in my career to ever be on that particular committee, and so I offer no apologies for these names. But these are Damascus sulcus and Baghdad sulcus and so on. They're very long features, and they are bounded by a kind of a pentagonal region that is fractured and therefore a kind of a singular plate separate from the rest of Enceladus. The South Pole is in here, and the material is all pouring out from this region. And so this amazing plume of Enceladus actually is the result of gas and grains, dust and ice, merging together from a number of individual jets coming off of the surface. There may be potentially about 100 individual jets, or some of this material may be coming out in curtains that are aligned with the fractures. I like this image because it's one of a couple in which the jets of material are being illuminated by the sun in the background, and Enceladus is being illuminated by Saturn shine, by the light of the sun bouncing off of Saturn and back onto Enceladus. And so these are individual fine jets that then merge to make the plume, and they come from this very tortuous geology here in the South Polar region. I like to say that Enceladus is more like Europa than Europa is, because we think of Europa as being the fractured satellite, but really this is the most intricate and complex kind of fracturing I think that we can see in the solar system today, at least among the icy moons. And if we look even closer, that, by the way, is an image that stretches about 500 kilometers from side to 300 kilometers from side to side. This is now a different scale. Here's just a kilometer, 2/3 of a mile, and you see these intricate fractures break up into even smaller ones, from which evidently material is leaking out of the interior. These are the highest resolution images. To get these, the spacecraft had to fly really close, tens of kilometers, and the spacecraft had to be rolled so that you would take out the smear associated with the movement of the features as the spacecraft zipped by. And so here I want to actually give a shout out to a part of the imaging team. The imaging team is led by Carolyn Porco at Space Science Institute, but Paul Helfenstein and colleagues who designed this image sequence are actually at Cornell University. So that's my shout out. Now you see here this fan-shaped feature above this crevice. Evidently gas and dust is coming out and blowing material away, creating that fan. This is a kilometer, and here this is just half a kilometer. So these features are maybe, you know, the size of the room, something like that. Really incredible images. And you see that there are these pinnacles with material that has been deposited on top. Probably, you know, with the low gravity, you get fairly substantial sized boulders coming out and then falling and landing on the top here. So this is an incredible fairyland fantasy type topography that we don't really have experience with elsewhere. And then in the north, there's no evidence of plume. The geology is very different. It's heavily cratered. Cassini imaged this later in the mission when the sun had moved from the south to the north as we went through autumn. It was winter in the north and then spring in the north. But you see that these craters are cut through by these fractures, indicating that Enceladus has been subject to stresses, being bent and pushed and twisted over its history, a clue to where this energy is coming from. And finally, to put everything together, Cassini took this image of Enceladus and the E-ring. You can see the plume feeding material into the E-ring. And so indeed, Enceladus is the source of that tenuous ring. So after all of these investigations and some remote sensing of the plume were done in the first couple of years, there was a very clear desire to fly through the plume. And the reason for that is that Cassini carried with it two instruments that could actually directly sample both the plume, gas, and grain material. And these instruments are called mass spectrometers. One of those mass spectrometers, called the ion-neutral mass spectrometer, we have here the principal investigator of that instrument, Hunter Waite, and I'm going to talk a lot about the results of that, because they're critical in understanding why we think Enceladus is habitable. Now, what a mass spectrometer does is it essentially analyzes the masses of atoms or molecules that are introduced into the instrument. And the way it does that is by electrically charging the material that comes in, either through, in this case, through direct collisions, because Cassini is moving quickly through the plume. Once these are charged, and they're usually singly charged, so you lose one electron, for example, then these are passed through either a magnet or an electric field, a magnetic field or an electric field, and that will cause the particle trajectories inside the instrument to bend. The lighter atoms or molecules, the ones with fewer protons and neutrons, are going to bend more in that electric field because they're singly charged, but they're lighter in weight, so they can be pulled more by the field. The heavier atoms or molecules are going to be turned less by the magnetic field, deflected less by the magnetic or the electric field. And so these atoms and molecules spread out according to their mass. Here we're looking at a diagram where this might be carbon dioxide, which has a carbon atom and 2 oxygen atoms. Carbon has 6 protons, oxygen has 8 protons, and then their most common isotopes. Remember, the elements can have different flavors, the number of neutrons being the different flavors or isotopes. So carbon most commonly has 6 neutrons, sometimes 7. And oxygen typically has 8. Sometimes it can have more. So you would expect to see a mass of 44, and with some heavier isotopes with more neutrons, you might have 45 or 46. So the 44 is deflected the most, the 46 is deflected the least. But something with a mass of 28, like carbon monoxide, is going to be deflected even more, and so it's going to be spread out along this detector. And so essentially the mass spectrometer then gives you a map of the abundance of these particles, atoms or molecules, as a function of their molecular or atomic weight. So there were 2 mass spectrometers on Cassini. Neither one was there for Enceladus. We know the plume was there, and so the INMS instrument, which I've already mentioned, was there to analyze the atmosphere of Titan. And then the cosmic dust analyzer was there to pick up dust in the Saturn system and also the Jupiter system, which Cassini flew through on its way to Saturn. This mass spectrometer breaks up ice grains and dust grains that collide with this plate. As the particle hits that, as Cassini flies through the material, through the plume, when a particle hits that plate and is broken up, it triggers electronically the instrument, so that essentially this only reads information when dust particles are coming in. And so essentially you know, okay, there's a dust particle or there's an ice particle, so that the mass spectrum you're getting is principally from the particles and not the gas. The INMS measures the gas. And so Cassini has instruments that can measure both what's in the vapor phase and what's in the solid phase, in this case coming from the plume. So very early on, after the fly-throughs of the plume began, the INMS instrument, the gas mass spectrometer, discovered that the plume is not only water vapor, but has organics present. And this is a cartoon from a paper by the INMS team, which shows the amount of signal versus the mass in what are essentially atomic mass units. So water would be 18, carbon monoxide would be 28. And different species are shown. Now, there are several peaks for many of these species because as they enter the instrument at high speed, they're broken up. And the pattern of their breakup helps the mass spectrometry team to identify which species they are, because there are many different species that may have the same molecular weight. For example, carbon monoxide and molecular nitrogen both have a weight of 28 mass units, or Daltons. So very much like throwing a pizza against the wall versus throwing a glass vase against the wall, those two things are going to fragment in different ways, and that fragmentation pattern helps you to identify the species. So here's water in blue, here's methane and ammonia in green, carbon dioxide in red. Of course, they don't come in colors in the mass spectrometer. This is based on the analysis. And organic molecules, carbon-bearing molecules with 2 carbons, 3 carbons, 4 carbons, and 6 carbons. So immediately, it was clear that wherever this plume is coming from inside Enceladus, whether from the crust or something deeper, it's carrying with it organic molecules, something we don't yet know about Europa, and which is critical to know, but we now know since 2008 about Enceladus. The Cassini cosmic dust analyzer, the dust mass spectrometer, then was able to measure the presence in the ice grains of sodium and potassium, which are shown here. Here's sodium clusters shown in yellow. Now, they also measure the molecular mass, but their instrument works in such a way that they bounce these atoms and molecules between 2 electrically charged plates. And so the mass is determined from the time of flight between those plates. So that's why this graph is plotted this way. But the yellow areas are sodium clusters, and they also found potassium and chlorine. So there is salt in the ice grains. And there's more salt in the largest ice grains. In fact, it's up to 2%. Seawater is 4% salt. Water ice itself doesn't dissolve salt. And so just the fact that there is this much salt in the ice grains immediately says that they are frozen liquid water, water that was liquid inside Enceladus. As it came out in the plume, it froze and retained the salt. That was the first indication that there's liquid water inside of Enceladus. And then at higher mass, these are probably very high mass organic compounds with lots of carbons in them, but it's difficult to tell what their identity is with this instrument. So where's this liquid water coming from? Is it trapped in the ice, or is there a global ocean? The first indication that there is a global ocean came from Cassini and from measuring the change in the velocity of the spacecraft as it passed by Enceladus in different directions along the South Pole, the North Pole, and so on. By measuring the change in speed of the spacecraft accurately from the Earth, by looking at the Doppler shift of the signal, you can determine the density in various places around Enceladus. And the data indicated that under the ice, there's a region of slightly higher density, not as dense as rock, which we have assumed is at the center, and it should be at the center because we know there's rock, and rock is denser than ice. But in between the rock and the ice, there is a layer of slightly higher density, which is inferred to be an ocean. In a little bit, I'll give you a much better piece of evidence for the ocean. Now, the other line of evidence that not only is there an ocean, but that ocean is interacting with the rock at the base comes from another discovery by the Cosmic Dust Analyzer of grains of nearly pure silicon. Here's another spectrum from the Cosmic Dust Analyzer on Cassini. It's dominated by silicon and by oxygen with a 1:2 ratio, and so that's silicon dioxide. Very, very small particles and nearly uniform in size. And the team, the Cosmic Dust Analyzer team, inferred that to get very tiny particles that don't have much size variation, one probably had a suspension of these particles in the ocean that were shot out quickly enough that they could not agglomerate. So where does that suspension come from? Well, the best guess would be that water is getting into the rock underneath, deep in Enceladus. It's leaching silicon dioxide out. And as the water cools off coming out of the rock, that silicon dioxide, which was dissolved in the hot water, has to precipitate out in the cold water and then is shot out into space. But why is there silicon dioxide? Well, one possibility is that there is not only a heating up of the water by the rock, but there are actually chemical reactions of the water and the rock. For example, one could have phaolite, which is a kind of olivine with iron and silicon and oxygen, reacting with water to make magnetite, which is iron and oxygen, plus silicon, and O2 in the form of silica or silicon dioxide, plus hydrogen, the leftover from the water. This is a hydration reaction or a serpentinization reaction. It happens at the seafloor of the Earth. We can't see the olivine or the phaolite or the magnetite. We know there's water there from the plume. We know there's silica there from the CDA discovery. Is there hydrogen to accompany that silica? And that question is so important because it would tell us that there's active chemistry, active cycling and reaction of water with rock. So in the very last fly-through of the plume in October of 2015, the INMS instrument, the gas mass spectrometer, was used in a mode that would allow it to detect hydrogen that is not being produced by collision of water inside the instrument, because that's always a concern, but in fact would be able to detect native hydrogen from Enceladus. And the result of this fly-through, which was the closest to Enceladus of any that were inside the plume, just 49 kilometers, resulted in the discovery of molecular hydrogen, which is a major discovery by the INMS team led by Hunter Waite. And it clinches, I think, pretty definitively the notion that there is this type of reaction going on at the interface between the ocean and the rock itself. And is there other evidence for these kinds of reactions? The answer is yes. You can also have the olivine reacting with water and carbon dioxide to make other minerals plus methane. We can't see the minerals, but we do see the methane through the INMS data. We see the carbon dioxide as well. So we have two different kinds of serpentinization reactions that are producing gases that we actually see coming out of Enceladus, and that's pretty convincing. But why does Enceladus have this heat? How is it producing enough heat to react water and rock in this way? And the answer can't be that it has this heat from its original formation, because it's just too small a body for that. It would cool off too quickly. But Enceladus is in a non-circular orbit around Saturn, and because of that, it gets tugged and pulled by the gravity of Saturn. To understand this, yes, I did this on my blackboard and then photographed it. I lost patience with trying to do this on PowerPoint. So here's Saturn, here's Enceladus. Remember, the force of gravity goes inversely as the distance squared. So although on average Enceladus feels a particular gravitational force, the near part of Enceladus feels a stronger gravitational force than the far part. The part that's facing Saturn is the near part. And so you can think of a gradient of the gravitational force, which would just be taking the derivative of this to get a tidal force, which goes as 1 over the distance cubed. So that tidal force, because it's stronger on the near side, because the gravity is stronger on the near side and weaker on the far side, the gravitational pull of Saturn, is going to tend to distort Enceladus into the form of an oblate shape like this. That oblate shape by itself would not produce heating if it were not for the fact that the orbit of Enceladus is eccentric, so that it spends some time closer to Saturn and some time farther from Saturn. Because the tidal force goes as 1 over the distance cubed, whereas the gravitational force goes as the distance squared, the tidal force dominates and becomes stronger, relatively speaking, when closer to Saturn, and so it actually stretches Enceladus out more. So Enceladus goes from more oblate to less oblate, as if you were squeezing a tennis ball. And furthermore, because this orbit is eccentric, Enceladus actually moves faster in its orbit when it's close to Saturn, slower when it's farther away. That's Kepler's law, Newton's law. And because the rotation rate of Enceladus is a constant, this variable movement around Saturn, this variable speed, means that this shape, this bulge, is going to twist or rotate back and forth as Enceladus moves around Saturn. And that creates an additional twisting motion, both of which, because Enceladus is not perfectly elastic, leads to heating. It's like taking a piece of clay or Play-Doh and squeezing it repeatedly. It will heat up. Now, this nodding back and forth is something that our own moon does. We can see that if we take photographs of it in the night sky. the amplitude of this nodding motion that Enceladus experiences is actually 3 times larger based on Cassini observations than was expected. And the only way to get that very large amplitude motion is to imagine that the outer part of Enceladus, the part that we see with the images, is actually sliding over a frictionless layer underneath, so that the gravitational pull, the tidal force, is acting on a much smaller mass than the total mass of Enceladus. And that will allow that part to swing back and forth more than the entire body of Enceladus. That is the other piece of evidence that we have that Enceladus actually has an ocean. And so where is the tidal heating occurring? It's probably occurring in the cracks on the surface, and because there is this water-rock reaction going on based on the discovery of hydrogen at the interface between the ocean and the rock, that will cause the rock itself to be fractured, allow water to pass through it, and it makes the rock less elastic. It makes it much weaker and allows for tidal heating, as suggested in this painting by Chris Glein, a colleague at Southwest Research, allows for tidal heating to occur in the core as well. So it looks like the energy source for Enceladus is pretty well understood. And furthermore, if in fact we have interpreted these Cassini data right, the ocean bottom of Enceladus probably looks very much like areas on the Earth's seafloor that are called off-axis hydrothermal systems, where very hot alkaline water is pouring out from the seafloor and reacting with minerals, and also reacting with water that is a different alkalinity. The water coming out of these systems on the Earth's seafloor are very alkaline. The ocean water is more neutral in pH. We have strong evidence from Cassini that the Enceladus water coming out is alkaline as well. So everything we see from Enceladus is telling us that at the base of the ocean, there's a hydrothermal system very much like that on the Earth, these off-axis hydrothermal systems, which are places that abound with life and might in fact be places where life actually began on the Earth, because there's a lot of chemical energy present there. So Enceladus has a salty ocean, it has organics, it has an energy source, and it has a hydrothermal system where water and rock are reacting to produce potentially food for microorganisms. These hydrothermal systems are restaurants at the bottom of the ocean. And so of the 3 ocean worlds that you're hearing about in this series in our solar system, Enceladus is probably the one that is most accessible in terms of ocean material, and the one that we know the most about. Europa is much larger. Its ocean, and we know it has a liquid water ocean, its ocean is much more voluminous, but we don't know anything about it yet, and we won't until Europa Clipper gets there. Titan may have a deep liquid water ocean, but almost certainly inaccessible from the surface. The interest in this are the methane seas that you'll hear about in that talk. Even though Enceladus is much smaller than either of these, everything that Cassini has told us is that it has the ingredients and the energy sources and the kinds of reactions needed to support life. So how do we detect that life? Well, the answer is that one can go back and do exactly what Cassini did, fly through the plume of Enceladus. But Cassini's instruments, particularly its mass spectrometers, designed in the 1980s, just didn't have the resolution necessary to be able to see the kinds of species that we want to see to be able to detect life and learn more about the habitability of the ocean. Just by way of example, the Cassini INMS instrument was limited to determining the masses of molecules to their unitary masses, their integer masses. You could tell whether something was 28 or 29. But different molecules that have the same total number of neutrons and protons actually have slightly different molecular masses, because when these things come together, when the protons and neutrons bind together, the so-called binding energy takes away some of the mass. So you actually have fractional masses for carbon monoxide and nitrogen in any of these species that are different from each other. And so an instrument that Hunter Waite is flying on the Europa mission called Mass Specs, and could be flown back to Enceladus, can distinguish very fine differences in mass. You see the scale now is on the sort of 0.01 level that would allow us to see a whole suite of biological molecules, including amino acids, fatty acids, and so on. Here's another type of instrument that could be flown back to Enceladus as well. The next generation of the CDA, you see fatty acids here, you see amino acids, all in very, very sharp relief in this mass spectrum. So I'm not going to go through how we would look for life, but the essential point is to look for the molecular patterns of the amino acids and other basic biological molecules and see whether those abundance patterns correspond to what we would expect for life or whether they look more like the random pattern that you would see if they were manufactured in nature in the absence of life. And we also need to go back and see whether some essential elements are present in Enceladus, including phosphorus and sulfur. The essential elements of life, so-called SNOPs, are carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Cassini has gotten CHNO for us, but not phosphorus and sulfur. And phosphorus in particular is crucial for life. It's very much overrepresented in life relative to its abundance in the cosmos by a factor of about 3,000, whereas all of these others, carbon, nitrogen, sulfur, are much closer to their cosmic abundances. Does Enceladus have phosphorus? It's critical to knowing whether life is present. And so, to close, Enceladus is the only world that we can say today that has a liquid water ocean that we have directly sampled. We have not sampled any other ocean in the solar system. It's remarkable that Europa has one. It's remarkable that Titan has seas. The only place we've touched and sampled and tasted is the ocean of Enceladus. Cassini's sampling of that ocean shows that it's habitable, and the next step is in many ways blindingly simple. The kinds of instruments that were successful on Cassini in their next generation form have the capability to go back into that plume, sample it again, and tell us whether the molecules coming out were manufactured by nature in the absence of life or manufactured by some kind of exotic alien garden of microbial delight. So let's go see. Thank you. So I can point, well, I've been told not to choose my own questioners. I don't.
Take the question and please wait for a microphone for the recording in case we have folks. Let's just start right up there. Okay?
The question is how fast the interaction was with the species that you were putting into the mass spec. I'm surprised that you're looking at molecules and not atoms. Typical orbital speed interactions are high enough that I would have thought the molecules would have disassociated.
No, actually, many of them stay intact. And, the Cassini's velocities varied from 17.5 kilometers per second through the plume to 7.5. And the INMS instrument in particular could see the change, the increase in the number of molecules as you went down to lower and lower velocities. And so the fact that you preserve molecular species as you go to lower velocities, but still at kilometers per second, is well documented. And it's also well documented in the literature that velocities of 4.5 to 5 kilometers per second will allow you to preserve those species. We actually want velocities because the ice particles have to be broken up by something in order to analyze them. So we want a high enough velocity to get the data from the dust mass spectrometer, but low enough to be able to preserve as much as possible the molecular signature. And 5 kilometers per second is kind of the sweet spot for that.
I'd like to know where we are on the spectrum of I wish I had something to, I'm thinking about building something to, I'm actually planning something to, we're scheduled to do it. And in terms of your estimate of when is the earliest possible time that this vehicle could be in the Saturn system, and when is the most pessimistic time?
Right. So Hunter Wade, who's the INMS PI for Cassini and also the principal investigator for mass specs, and myself led a proposal. I was the PI, Hunter was deputy PI, to do exactly what I've described. It was submitted to the New Frontiers competition this year. There was another proposal in competition from another group that involved instruments other than mass spectrometry. Neither one was selected for flight. And so I have a slide prepared for you. I won't step through this, but the next opportunity for New Frontiers, because we're not selected and because these medium-class missions are launched on small enough rockets that the flight time is 10 years, that our next opportunity with New Frontiers would get us the answer to this question in 2040.
So we wouldn't be there for 2040.
Right, unless we do this. But that's not what NASA's offering. And I have to say, I think this is a crisis because the outer solar system, and this is true for Jupiter as well, although Jupiter's somewhat better. You know, the outer solar system has turned out to be where the action is for life in many, many ways. And yet it takes so long to get there, and it's so expensive. And I also have to say that Arthur C. Clarke pointed this out in the Mariner 9 panel at Caltech that he was on in 1971, Mars and the Mind of Man is the book. And you can see in that book his quote in which he says, I believe that the frontier for the action as far as life goes has moved beyond Mars to the outer solar system. Now, there may have been life on Mars. I don't want to dismiss Mars. But here's a place where life could be present today and it's accessible to us, except it's 20 years away. Go back to a positive slide here. Yeah.
I have two questions. Silicon dioxide is to be molten, as you were explaining. What temperature would that have to be? And it seems to me, you know, that we're talking about a very cold body here.
Right. So SiO2 doesn't have to be molten in this case. What's happening is that water at about, I think, roughly 90 degrees Celsius, reacting with the rock will allow the reactions that produce SiO2 from olivine to occur. But the SiO2 is never molten, and it's leached out of the rock simply by contact with the hot water. So the water reacts to hydrate the rock, and that produces the SiO2, and then that dissolves into the hot water. As that hot water cycles back out into the colder ocean, the SiO2 is no longer soluble, and so it just precipitates out as a colloidal suspension. Yep, and the energy source is tidal heating. It's the tugging and squeezing of this body that is not circular anymore because of tidal forces, and that oblateness, it varies as a function of distance around the orbit.
And my other question, thank you, is the smoother surface of Enceladus, is that the surface that is facing Saturn?
So yeah, well, the smoother part is actually the south polar region, principally, and it extends up. Let's see, you know the orientation of the lower latitude smoother part. I don't know what that is either, but the important, the tectonically active part, the part that's geologically active, is really at high southern latitudes, and it's bounded by this sort of weird pentagonal fracture system at about 60 degrees latitude south.
Do we have questions in the overflow room?
No, thank you.
I'm just wondering, I see a lot of
Yeah.
I see oxygen all the time.
Yeah.
No, I mean, is there anything to do with oxygen as far as we know it in our world, other than chemical reactions?
Right. So there's oxygen there. Oh yeah. The questioner said he saw a lot of oxygen in those diagrams, and does that oxygen have anything to do with the way it's created on our world, namely the Earth? And of course, most of the oxygen you saw there was bound up either in water or SiO2 or other things that we have not, none of the Cassini data, I believe, shows molecular oxygen. On the Earth, of course, it's mostly photosynthesis by plants, but if that were to suddenly go away tomorrow, which we would not want to have happen, there are other ways to produce molecular oxygen. Now, the interesting thing about Europa, relative to Enceladus is that Europa is embedded in a much more intense radiation environment where actually radiolysis produces a lot of molecular oxygen. And one thing that might be very attractive about Europa is that if that molecular oxygen gets into the ocean of Europa, it could be a very powerful oxidant and very powerful energy source. That's probably not going on, at least not to the same extent at Enceladus, because the environment around Enceladus is much quieter. There's much less radiation around Enceladus than Europa. I see one there.
I just had a quick question.
Yeah.
Hello, sorry,
Hi.
down here. Can you just talk about what it felt like personally when you saw that first image of the plumes on Enceladus? Just from a personal perspective.
Yeah, so when I first saw that, I thought to myself, how is it possible that we didn't see that with Voyager? Because as a graduate student, I remember going to Division of Planetary Science meetings where people had heroically stretched these Voyager images. Voyager had a Vidicon tube, which of course is ancient history today. And they'd stretch these images and could you sort of see a little something at the bottom? No, not really. And here Cassini comes along, and on its first try, there it is. And so, you know, that was really a shock, but it just hammered home how much more sensitive Cassini was. To me, the more visceral feeling came when the imaging team began to take images of these individual jets coming out of the bottom. And there are a number of images on the Cassini website that kind of look like rock concerts with, you know, these sort of shooting beams of light from the individual jets. And that really, really impressed me a lot. But the first images were, why didn't Voyager see this? Maybe it did.
I'll take one more question over there.
Say a living organism is found in this planet or
The moon, yeah.
yeah, then how will that change your perception or understanding of our place in universe, or the collective understanding of our place in universe?
So, how would the discovery of an organism in Enceladus change our perspective on the universe or the Earth? Philip Morrison, who was a relatively well-known physicist in the 50s and 60s at Cornell and MIT, famously said that the discovery of life on another world would change the origin of life from a miracle to a statistic. And I think that's the basic answer, that we have one example of the origin of life, which is that on Earth sometime 4 billion years ago. And that produced, or maybe there were other forms that it outcompeted, it produced one kind of life from the biochemical point of view. And so we have no idea how easy or hard it is for life to arise from non-biological chemistry. We have no idea how long it would take. We have no idea how restrictive the particular sets of molecules are that life like us uses. We don't know any of that. And finding a place where there is life that is present and is far enough from the Earth that it wasn't simply a contaminant, cross-contamination by asteroids, and Enceladus is far enough away. It would tell us that. But of course, it's a multi-step process. You have to find evidence that life is there. Then you need to go back with the kinds of elaborate instruments to be able to culture and study a cell. The plume is so tenuous that as you fly through it, you have almost no chance of getting a cell. You're getting the molecular debris of life. If you want to actually get the cells, you're going to have to go down and sample at the surface, sample the stuff coming out or even the ocean. So it's a multi-stage process. But imagine having a second example of life to study and to find out how different or alike to the Earth life it is. And then there are practical applications too, because there are biologists trying to synthesize additional nucleic acid bases that could function in sequence. There was an article about that recently. Nature is always more creative than scientists in the lab, and maybe it's created something really cool in Enceladus.
Let's thank our speaker one more time. thank you for joining us all tonight. If you're online, thank you for joining us, and we'll see you in February.